If you're looking for a way to efficiently grasp core principles of complex technical topics, well, today's deep dive gets right to the heart of a really fundamental challenge in distributed systems.
Yeah, we're talking about achieving consensus.
Exactly. Specifically, we're focusing on the Paxos algorithm, as Leslie Lamport laid it out in Paxos Made Simple.
It's a classic paper.
It really is. And our mission today is pretty straightforward. Provide a clear, concise understanding of its fundamental mechanisms for building, reliable systems.
Because in these distributed environments, things fail. Components go down, messages get delayed, and making sure everyone agrees on something. That's surprisingly tricky.
It sounds like it. So this deep dive will really unpack how Paxos tackles that specific challenge, giving a focused look at its core logic.
That's the plan.
Okay, so let's start by framing the problem. What exactly is the problem Paxos is trying to solve?
Right. So imagine you have this system, lots of different processes, computers, whatever, and they can all propose different values for something. Maybe it's the next command to execute or, the status of some resource.
Okay, multiple suggestions flying around.
Exactly. And the core goal of a consensus algorithm like Paxos is to make absolutely sure that only one of those proposed values gets definitively chosen, like stamped as the value.
Just one. That sounds critical.
It is. And there are a couple of other guarantees, really important safety guarantees. First, only a value that was actually proposed by someone can be chosen. The system can't just make one up.
Makes sense.
Second, as we said, only a single value is ever chosen. No ambiguity. And third, if a process, say, learns that value X has been chosen, then value X must have actually been chosen. No learning false information.
Okay, those sound like absolute must-haves for reliability. You mentioned safety. Is there anything else?
Well, there's also the idea of liveness. That eventually some value will be chosen and learned, progress has to be made. But honestly, for understanding Paxos core, Lamport really focuses on getting these safety properties right first. That's our main focus today, too.
Got it. Safety first. So how does Paxos structure this? Are there different parts to the system?
Yeah, Lamport defines 3 logical roles: proposers, acceptors, and learners.
Proposers, acceptors, learners. Okay.
Proposers, well, they propose values. Acceptors are the ones who sort of vote on or accept these proposals. And learners find out which value, if any, has actually been chosen by enough acceptors.
And can one machine be all 3?
Oh, absolutely. In practice, a single server or process often plays multiple roles, even all 3. But thinking about them separately really helps understand the logic, the flow of the algorithm.
Okay, that separation makes sense conceptually. What about the environment? What are we assuming about how these parts talk to each other?
Good question. We assume communication is asynchronous. Messages can take any amount of time. They can get lost, duplicated, arrive out of order. Basically, no timing guarantees.
Wow. Okay, that sounds challenging.
It is. We also assume what are called non-Byzantine.
Seems easy enough, but I sense a but coming.
Yeah, the big but is, what if that single acceptor fails?
Then no value can ever be chosen again. The whole system halts.
Exactly. It's a single point of failure. Totally unacceptable for a fault-tolerant system.
So we need more than one acceptor.
Right. We need multiple acceptors. And the core idea then becomes, a value isn't chosen just because one acceptor likes it. It's chosen only when a large enough set of acceptors accept it.
Large enough set. How large?
Paxos defines this as a majority, more than half of the acceptors.
Okay, a majority. Why a majority specifically?
Because of a fundamental property. Any 2 majorities must overlap. They have to share at least one common member.
Oh, right. Simple set theory. If you have, say, 5 acceptors, a majority is 3. Any 2 groups of 3 must share at least one acceptor.
Exactly. And that overlap is the key to preventing the system from choosing 2 different values. If one value gets a majority, any attempt to choose a different value later will have to convince at least one acceptor that already accepted the first value. That's where the control mechanism comes in.
Okay, but wait. If an acceptor is part of a majority for value A, and then later someone tries to propose value B, can the acceptor just switch? Or does it need to stick with A?
Good point. For the system to make progress, especially if the first proposal attempt fails partially, acceptors must be able to accept more than one proposal over time. They can't just lock onto the very first thing they see.
So they can change their mind, in a sense.
Not exactly change their mind about what was chosen, but they can accept later proposals. This means we need a way to distinguish between different proposals.
Sequence numbers. or something like that.
Precisely. Paxos uses proposal numbers. Every proposal consists of a number and the actual value being proposed. And crucially, these proposal numbers must be unique and totally ordered. Let's just assume for now we have a way to generate these unique numbers.
Okay, unique proposal numbers. How does that help ensure only one value gets chosen?
It leads to the cornerstone safety property, which Lamport calls P2. It states, if a proposal with value V is chosen, then every higher numbered proposal that is chosen has value V.
Let me unpack that. If we successfully choose value apple with proposal number 10, then any later proposal that also gets chosen, say number 25, must also have the value apple. It can't be banana.
Exactly right. The proposal numbers enforce that once a value is locked in by being chosen, subsequent chosen proposals stick with that value.
How is that property actually enforced, though?
Well, to ensure P2, Lamport introduces a slightly stronger intermediate property, P2A. It says, if a proposal with value V is chosen, then every higher numbered proposal accepted by any acceptor has value V.
Okay, so not just chosen proposals, but any proposal accepted by any acceptor later must have the same value. Why is that needed?
Because a proposal has to be accepted by a majority before it can be considered chosen. So controlling what acceptors accept is the way to control what eventually gets chosen.
Right, control the inputs to control the output.
Precisely. But now we hit a snag with asynchrony. Remember that simple idea, maybe P1 we could call it, that an acceptor should just accept the first proposal it receives? Well, imagine value apple with number 10 gets accepted by a majority, so it's chosen. But then, due to network delays, a proposal for banana with number 15 arrives late at one of the acceptors that was part of the apple majority. If that acceptor just followed the simple accept the first proposal I see with a higher number rule, it would accept banana number 15.
And that would violate P2A because we already chose apple with number 10.
Exactly. So P1, that simple rule, doesn't work. We need something stronger. This leads to property P2B.
Okay, another one, P2B.
P2B states, if a proposal with value V is chosen, then every higher numbered proposal issued by any proposer has value V.
Issued. So even before it gets accepted, the proposer itself must use the chosen value.
Yes. If P2B holds, then P2A must hold, since a proposal must be issued before it's accepted, and therefore P2 holds. So ensuring P2B is the goal.
How does a proposer know what value was previously chosen, especially in this asynchronous world with potential failures?
That's the million-dollar question. And the answer lies in the core mechanism of Paxos. Lamport uses inductive reasoning, but it boils down to ensuring an invariant holds before any proposer even issues its proposal. This invariant is P2C.
P2C. This sounds like the important one.
It really is. P2C says roughly, for any proposal N with value V that a proposer wants to issue, there must exist some majority of acceptors. Let's call it set S, such that either A, no acceptor in S has accepted any proposal numbered less than N, or B, if acceptors in S have accepted proposals numbered less than N, then V must be the value of the highest numbered proposal among them.
Whoa, okay. Let me try that. Before I, as a proposer, can even send out my proposal, number N, value V, I need to know that a majority of acceptors satisfies a condition. Either they haven't accepted anything earlier, or if they have, my value V must match the value of the latest proposal they've already accepted.
You got it. If the proposer can guarantee this P2C condition before issuing its proposal N, then P2B will hold and safety is maintained.
So how does the proposer ensure P2C holds? It needs to talk to the acceptors first, right?
Exactly. This leads directly to the famous two-phase approach of Paxos.
Phase 1 and Phase 2. Okay.
Phase 1 is called prepare. The proposer picks a new, unique proposal number N, higher than any it's used before. It sends a prepare request with this number N to a majority of acceptors.
What's in this prepare request?
Two things, essentially. First, it's asking the acceptor, please promise me you won't accept any proposal numbered less than my number N from now on.
Okay, a promise for the future.
Second, it asks, and by the way, what is the highest numbered proposal, if any, that you have already accepted? The acceptor should respond with that proposal's number and value.
So gather information about the past and secure a promise for the future. What happens next?
The proposer waits. If it receives responses, promises, and maybe info about past proposals from a majority of acceptors, then Phase 1 is successful. It now knows P2C can be satisfied.
And it knows what value it has to propose, potentially.
Yes. This is crucial. The proposer looks at all the responses from the majority, If any of those responses indicated a previously accepted proposal, the proposer must choose the value associated with the highest proposal number reported back.
It's forced to adopt that value.
It is. If it wants to proceed with proposal number n, it must use that value. If none of the acceptors in the majority reported having accepted any prior proposal, then the proposer is free to use the value it originally wanted to propose.
Okay, so it figures out the value v based on the phase 1 responses.
Yeah.
Then what?
Then it moves to phase 2. Accept. It sends an accept request to that same majority of acceptors, or potentially more. This request contains the proposal number n and the chosen value v.
And what do acceptors do when they get these requests? Let's start with prepare.
When an acceptor gets a prepare request with number n, it looks at the highest numbered prepare request it has already responded to. Let's say that was number p. If the new request's number n is greater than p, the acceptor makes the promise not to accept proposals below n, and sends back the highest numbered proposal it has actually accepted so far. It also remembers n as the highest promise it has made.
What if n is not greater than p?
If n is less than or equal to p, it means the acceptor has already promised someone else it wouldn't accept proposals numbered n or lower. So it ignores the new prepare request, or at least it doesn't make the promise.
Okay, that enforces the promises. Now, what about the accept request in phase 2?
When an acceptor receives an accept request for proposal number n with value v, it will accept it only if it has not already made a promise in phase 1 to a different proposer for a proposal number greater than n.
So that promise it made in phase 1 is binding. This is captured in Rule P1A, right?
Exactly. P1A basically says, an acceptor can accept proposal n if and only if it hasn't promised to ignore it. By responding to a prepare request with a number higher than n, this rule, P1A, effectively replaces that naive P1 idea we discussed earlier.
Got it. So the prepare phase sets a lower bound on acceptable proposal numbers.
Precisely. And there's an optimization Lamport mentions. If an acceptor gets a prepare request for number n, but it has already promised a higher number Pn, it can just ignore the n request. No need to even send a negative reply. Similarly, if it receives an accept request for n but has already promised Pn, it ignores the accept request.
Keeps things efficient. And this brings us back to the need for stable storage.
Yes. For this whole thing to survive crashes, the acceptor must persistently store, at minimum, the number of the highest prepare request it ever promised, P in our example, and the number and value of the highest numbered proposal it actually accepted. Without that, it would forget its promises and votes after restarting, breaking the safety guarantees.
Okay, that two-phase dance is intricate, but seems logically sound for ensuring only one value gets locked in. Now, how do the learners find out what value won?
Right. Choosing is one thing, learning is another. Once a proposal is accepted by a majority, it's officially chosen, but the learners don't automatically know this.
So how do they learn? Do the acceptors tell them?
That's one way. Every acceptor, when it accepts a proposal, could broadcast that fact to all learners.
Seems noisy if there are lots of acceptors and learners.
It can be. Very high message overhead. So other strategies exist. You could have acceptors only report their acceptances to a specific distinguished learner. That learner is then responsible for telling everyone else.
But wouldn't that make the distinguished learner a bottleneck or a single point of failure?
It could, yes. So often a compromise is used. Acceptors report to a set of distinguished learners, providing some redundancy. The exact mechanism is often an implementation detail balancing efficiency and fault tolerance.
What if messages get lost? Even if a majority accepts, maybe the messages to the learners just disappear.
That's a real possibility in an asynchronous network. A learner might simply never hear about a chosen value.
So what can it do? Just wait forever?
No, learners can be proactive. If a learner suspects a value might have been chosen but hasn't heard, it can essentially ask a proposer to start a new round of Paxos with a new proposal number. During phase 1 of this new round, the proposer will query the acceptors, and if a value is already chosen, that information will likely come out in the responses.
So initiating a new proposal can also serve as a way to discover the outcome of previous ones. Clever.
It's a way to probe the state of the system.
Okay, so we have safety choosing one value, and we have learning. What about progress? You mentioned liveness earlier. Does this two-phase process guarantee we'll eventually choose something?
No, not inherently. The core algorithm we've described guarantees safety, but it doesn't guarantee progress or liveness on its own.
Why not? What can go wrong?
It's possible for multiple proposers to get into a kind of duel that prevents any proposal from actually being accepted by a majority.
How would that happen?
Imagine proposer A starts phase 1 with number 10. It gets promises from a majority. But before it can send its phase 2 accept request, proposer B starts phase 1 with a higher number, say 11. Proposer B gets promises from a majority, maybe including some acceptors that promised A. Now, these acceptors have promised not to accept anything less than 11.
So when proposer A's accept request for number 10 finally arrives,
It gets ignored by those acceptors because they've already promised 11.
okay, but proposer B can now send its accept for 11.
Maybe. But what if, before that happens, proposer A comes back with proposal number 12?
Ah, I see. They could potentially keep leapfrogging each other with higher proposal numbers, constantly making acceptors promise higher numbers, but never actually getting an accept message through for the current number before the next prepare arrives.
Exactly. This is sometimes called dueling proposers or live lock. They keep preparing, but no one ever successfully accepts. No value gets chosen.
So how do practical systems solve this? They must make progress eventually.
Yes. The standard solution is to introduce the concept of a distinguished proposer, often called a leader.
A leader, okay.
Only the leader is allowed to initiate proposals. If other processes want to propose something, they send it to the leader. As long as the leader is alive, can communicate with a majority of acceptors, and uses sequentially increasing proposal numbers, its proposals will eventually be accepted.
Why eventually? What if another proposer tries to interfere?
If the leader receives a rejection in phase 1 or 2 because some acceptor promised or accepted a higher number, maybe from an old leader or a malfunctioning node, the leader simply backs off, chooses an even higher proposal number, and retries phase 1. Eventually, its proposal number will be the highest, and it should succeed.
But choosing this leader, that sounds like another consensus problem.
It is, in a way, and this ties into a famous result in distributed systems, the Fisher, Lynch, and Patterson FLP impossibility result. It basically proves that in a purely asynchronous system prone to even one crash failure, no deterministic algorithm can guarantee both safety and liveness.
So you can't have a perfect algorithm that's always safe and always makes progress.
Not deterministically in a purely asynchronous model. That's why practical leader election often relies on things like timeouts or randomization elements that step slightly outside the pure asynchronous model. But the key takeaway is, Paxos's core safety guarantees hold regardless of leader election success or failure, or even if there's live lock. Safety is paramount. Progress is handled typically by the leader election layer on top.
That's a really important distinction. Safety is always there. Progress needs this extra leader mechanism.
Correct.
So stepping back a bit, how does this look in a real implementation? We have these roles.
Right. In a real system, you have a network of servers. Each server process will typically run the code to act as an acceptor, a learner, and potentially a proposer.
And one of them gets elected leader.
Usually, yes. A leader election protocol picks one server to be the leader. That server then acts as the primary proposer, driving the consensus process. It might also take on a primary learner role.
And they communicate via network messages.
Standard messages for prepare, promise, accept, accepted, etc.
And the acceptors need that stable storage we talked about.
Absolutely critical. They need to write the highest promise made and the highest proposal accepted to disk or some other persistent medium before sending replies to ensure they remember across crashes.
What about generating those unique proposal numbers?
A common technique is to give each potential proposer a unique ID and have them generate proposal numbers that combine a sequence number with their ID. For example, proposal number 15, server 3, would be higher than 14, server 1, and also higher than 15, server 2. This ensures uniqueness and total ordering. Each proposer just needs to remember the highest sequence number it personally used.
Okay, that makes sense. So this core consensus algorithm, it lets a group agree on one value. How is this used to build bigger things? Lamport talks about state machine replication.
Yes, this is arguably the most powerful application of Paxos. State machine replication is a fundamental technique for building fault-tolerant services.
How'd it work?
The idea is simple. You have multiple servers, and each server runs the exact same deterministic program, the state machine. If you can guarantee that all servers execute the exact same sequence of commands in the exact same order, then they will all maintain identical state.
Like database replicas, kinda.
Exactly like that. If they all process transaction 1, then transaction 2, then transaction 3, they'll end up with the same database state, even if some servers crash temporarily. Clients can talk to any non-crashed server and get a consistent view.
And relying on just one server is bad because...
Single point of failure again. It crashes, the service is down, replication is key for fault tolerance.
So how does Paxos fit in? How does it ensure they execute commands in the same order?
By running a separate instance of the Paxos consensus algorithm for each slot in the command sequence.
Like multiple Paxos runs.
Potentially infinite runs, yes. To decide the first command in the sequence, all servers run Paxos instance #1. To decide the second command, they run Paxos instance #2. To decide the ith command, they run Paxos instance I.
And the value being proposed in instance I is the actual command for that slot.
Precisely. A client sends a command, say, update account X, to the current leader. The leader decides this should be, say, command number 500 in the sequence. It then initiates Paxos instance #500, proposing update account X as the value.
And all the servers participate as acceptors and learners in all these Paxos instances.
Typically, yes. Assuming a fixed set of servers for now, the leader acts as the distinguished proposer for all these instances.
Does the leader need to know the command before starting phase 1 for instance 500?
Not necessarily. That's a key optimization. The leader can run phase 1 for instance 500, and maybe 501, 502, just by sending a prepare request with the proposal number. It only needs to decide on the actual command, the value v, when it gets the promises back and initiates phase 2. This gives it flexibility.
Okay, that sounds efficient. What happens if the leader fails?
Failure recovery. So a new leader gets elected. Its first job is to figure out where the previous leader left off. The new leader acts as a learner for all past Paxos instances. It runs phase 1, prepare requests, for a range of sequence slots, maybe all the slots it isn't sure about, plus some future ones.
And the acceptor's responses will tell it which commands were already chosen for which slot.
Exactly. It might find out that commands 1 through 498 were chosen, command 499 was proposed but maybe not fully accepted everywhere, and command 500 was never even proposed.
So what does the new leader do?
It needs to ensure commands 499 and potentially others get fully chosen. It runs phase 2 for any instance where phase 1 revealed a value that needs finalizing. If it finds a gap, say slot 499 never had a value chosen, it needs to fill it.
Fill it with what?
Often, it will propose a special no-op command, a command that doesn't actually change the state machine's state, but just fills the sequence slot. It runs Paxos instance 499 to get this no-op chosen.
Why bother with a no-op? Why not just jump to 500?
Because all servers must execute the commands in the exact same sequence. If server 1 thinks command 500 is the 499th command, while server 2 thinks it's the 500th, their states will diverge. Filling the gap with a no-op ensures everyone agrees on the sequence numbering before executing command 500.
Got it. Sequence integrity is paramount. So the new leader fills gaps with no-ops, finalizes any pending commands, and then starts proposing new client commands for subsequent slots.
Exactly. It picks up where the old leader left off and continues driving the sequence forward.
You mentioned a leader might propose commands for slots 501, 502 before 500 is even confirmed, pipelining.
Yes, leaders often do that for performance. They might initiate phase 1 or even phase 2 for multiple future slots concurrently. This speeds things up, but means if the leader crashes mid-pipeline, the new leader might find temporary gaps that need filling with no ops. But again, safety is preserved. The final sequence will be consistent.
Is there an optimization for the new leader's recovery? Running phase 1 for potentially hundreds of slots sounds slow.
There is. A new leader can often run phase 1 for many instances, say slots 500 through 1000, using a single, compact prepare message. An acceptor only needs to reply with detail if it actually accepted something in that range. Otherwise, it can give a simple nothing accepted in this range promise. This makes recovery much faster.
So during normal operation, when the leader is stable, what's the actual cost of getting a command agreed upon?
It's essentially the cost of phase 2 of Paxos. The leader sends accept requests to a majority and they respond. Lamport argues this is close to the minimal communication needed for any fault-tolerant consensus in an asynchronous system. Phase 1 happens less frequently, mainly during leader changes or contention.
What if leader election goes wrong? Maybe it fails, or two servers think they're the leader.
If leader election fails and there's no leader, the system typically just stalls, no new commands get proposed. Progress stops, but safety is fine. If two servers think they're the leader, they might start dueling proposals for the same instance, potentially causing live lock for that instance, as we discussed. Again, safety holds. They won't choose different commands for the same slot, but progress might be temporarily halted until the leadership situation is resolved.
Safety, safety, safety. That seems to be the bedrock.
It absolutely is.
One last thing on state machines. What if the set of servers itself needs to change? Add a new replica, remove a failing one.
Ah, dynamic membership. That's a more advanced topic, but Paxos handles it elegantly. The configuration of the system, the list of current servers participating as acceptors can itself be part of the replicated state machine's state.
So changing the configuration is just another command.
Essentially, yes. You propose a special change configuration command, e-jumping add server X, remove server Y. This command is decided upon using Paxos run by the current configuration. Once chosen, all servers execute it, update their view of the active membership, and the next Paxos instance uses the new configuration. It allows for quite sophisticated reconfiguration while maintaining consistency.
Wow. Okay. That's powerful.
It really ties the whole system together.
All right, let's try to summarize this deep dive then. We've really dug into Paxos, exploring how it tackles consensus in these tricky distributed environments with failures and delays.
Yeah, the core is that two-phase commit process, prepare and accept, involving the proposers, acceptors, and learners. It's all built around ensuring safety, specifically that only one value gets chosen.
And we saw how this fundamental consensus is then used as a building block, particularly for state machine replication, letting us build really robust fault-tolerant services where multiple servers maintain a consistent state.
It's a foundational algorithm for a reason, hugely influential.
So maybe a final thought for our listeners to chew on. Given all this complexity we've discussed, the phases, the properties, the edge cases, what are the real-world engineering challenges? What trade-offs do developers face when actually trying to build and deploy a Paxos-based system in production?
That's a great question, and maybe another angle. We assumed non-Byzantine failures. What happens if that assumption breaks down? What if nodes can be malicious? How does that change the game for achieving consensus? That opens up a whole different area of research and system design.
Definitely food for thought.
Mm-hmm.
The pursuit of reliable distributed systems clearly involves deep challenges. For anyone wanting to go deeper, Leslie Lamport's original Paxos Made Simple paper is the place to start, and there's a vast amount of research building on it since.